Dear students, welcome back to NPTEL online certification course on analog electronic circuit. Myself Pradeep Mandal from E&EC department of IIT Kharagpur. So, to continue this course, today's topic of discussion it is amplifier with active loads. We may be having multiple amplifiers, but primarily we will be talking about common emitter and common source amplifier today. Compared to our overall weekly plan, we are in week 6, I should say module 6, and we are in fact, we already have completed these two subtopics, namely multi-transistor amplifiers and then cascade amplifiers. And today we are going to talk about amplifier with active load. In fact, incidentally, when we talk about active load, the amplifier it is having multiple transistors. So, you may say that this is also a special kind of multi-transistor amplifiers, but we like to explicitly say that it is having unique characteristic, where the passive load it is getting replaced by a load utilizing MOS transistor or BJT transistor. So, that is why though it is multi-transistor amplifiers, but basically characteristic wise the load part it is getting replaced by another transistor. Now, today what we are planning to cover it is under this active load amplifiers. We do have to start with, we do have motivation of using this active load, and then from that we will be talking about basic operation of amplifier having active load and their corresponding circuit analysis, including small signal model and then finding the gain or maybe intuitively explaining the gain and so on. So, and then we will be talking about practical circuits having the active load, and for both the basic operation as well as for practical amplifiers we do have two main amplifiers in our discussion. One is common emitter and common source amplifier. Numerical examples and design guidelines it will be covered in the next class. So, to start with, let us go for the motivation of going for active load. This is a recapitulation or recalling whatever we know about CE amplifier, and not only we will be talking about CE amplifier, but basic operation of the CE amplifier, just to say that what is its limitation of the voltage gain. In fact, if you recall that this is the main amplifying transistor, and it is at the input we do have the signal we are feeding along with the DC component. So, that the transistor it is in active region of operation. In addition to that, we also have the RC connected to the collector to the supply voltage VCC, and the connection of this RC it is such that the transistor here it is in active region of operation. So, this RC it is having dual role to play. First of all, it provides appropriate region of operation, and the second one it also converts the current into voltage, because primarily at the output we observe the signal in the form of voltage V out. So, by applying a voltage at the input port, namely at the base, it is given here, which is having a DC voltage along with the signal. We are changing the collector current with respect to its quiescent current, and that variation or change or the signal part it is getting converted from voltage to from current to voltage by this resistor RC. So, this resistor typically it is referred as load, and it is, if it is passive component, which is providing linear IV characteristic. Of course, it works fine, but to some extent it is having limitation to give the voltage gain. I should say rather it is having good gain, the CE amplifier, basic CE amplifier, it is having good gain. But in case if you want to enhance the gain further, then there is a scope of improving the gain, and that may be done by replacing this passive element by its active equivalent circuit. So, let us see that where the limitation it is coming from, particularly for the voltage gain. To come to the basic, at the base, what we are doing is we are changing the voltage at the base, or either we say base voltage or base to emitter voltage. And if you observe the base, the current flowing through the base terminal, say I B, instantaneous current having both DC as well as the small signal part, as function of V B E, which is also having a DC part as well as the small signal part. As you know that it is having exponential dependency. Now, this base current, it is getting converted into collector current, and that we may call capital I C. And this I C, it is flowing through this R C, and it is creating a drop across this resistor called V R C, and then we do have the supply V C C. So, V C C minus V R C, that gives us the V out. So, this is V C C minus V R C, and then this V R C, as I said that it is having R C, its expression is R C multiplied by I C. So, pictorially, if you see the output port characteristic, namely if we sketch the I C versus V out. So, you may recall for a given value of current at the base, the corresponding collector current it is having I V characteristic like this. So, in the active region the current I C, it is almost independent of V out, but then if you go very low, then of course, the device enters into saturation region, and then there is a significant, or I should say sharp dependency of the collector current on V out, or in this case incidentally that is V C E. Now, then if we consider the load line characteristic, as we have discussed, load line characteristic, it is given by essentially I V characteristic of this R C, and we have discussed that how we obtain this load line characteristic. Namely, if you plot the voltage, the current through this resistance R C with respect to its voltage across it, it is V R C. Actually, this load line characteristic is linear, but then to match the x axis, this V R C, instead of writing V R C, we prefer to write this as V C C minus V out. So, to match this x axis with this the V out, what we have done, or we in fact we have discussed that we do flip this x axis. So, that the characteristic it becomes in the second quadrant, and then after that we shift it. So, that then the load line, then we get the load line where the shift it is V C C amount. So, this point it is V C C, and then slope of this original I V characteristic, it was 1 by R C, and the slope of the transformed load line characteristic, it is minus 1 by R C. So, that is how we obtain this load line. So, the slope of this line, it is minus 1 by R C, and the amount of shift we have done here to get rid of this VCC part to match the V out axis with this V out axis, we have shifted this point here. So, that gives us this point of the load line characteristic, it is VDD. So, that gives the one edge of the load line VCC or VDD, in this case VCC, and the slope it is minus 1 by RC. That gives the other end of the load line, it is equal to VCC divided by RC. Now, we know that once we have this load line and once we have the device characteristic, intersection of these two characteristic gives us the final V out, and also of course, it is giving the corresponding current called IC. So, this IC and this V out, it is basically the solution point. Now, whenever we are giving a signal, as you may recall, whenever we are giving this signal with respect to a DC operating point, so that means we are changing the device characteristic up and down with respect to its actual the exponential relationship. That makes the device characteristic, namely the we call this is pull down element characteristic, it goes down or up. And as a result, since the operating point it is changing by varying this voltage, and incidentally that is also changing the V out, namely the output voltage, and that is how we are getting the output signal, right. Now, if you see that the gain starting from the input, which is getting converted into current I B, and then through the multiplication of beta, then we obtain. So, this I B, it is getting converted into I C by multiplying with beta, and then again by this load line, the signal part it is getting converted back into this voltage. So, I should say that we do have a voltage here, voltage it is getting converted into current, and then this current it is coming to this y axis, and then this load line characteristic it is converting back this current into voltage. So, we can say that we do have two reflectors, one is I B versus V B characteristic reflector multiplied by beta, and then we do have the other reflector. In fact, if you combine this multiplication and then this exponential relationship, namely if we plot the I C versus V B E characteristic curve, then of course, this is also exponential, but with it is having different scale because of the beta. So, this I C versus V B characteristic curve, it gives us one conversion from voltage to current. So, that gives us the current, and then this characteristic curve it is converting back this current into voltage. So, naturally the gain of this conversion, input to output gain, it depends on the conversion rate here, and then also it depends on the conversion rate at the other reflector. So, if I intuitively if I say that if the slope of this reflector it is very stiff, on the other hand if the slope of this reflector it is say very small, then we can get high gain. So, the mathematically you can say that gain, when you say gain, A V equals to G M into R C with a minus sign, right. So, since the gain it is G M into R C, and the slope of this line it is nothing but G M, and slope of this line on the other hand it is minus 1 by R C. So, I should say that the gain is essentially slope of this mirror multiplied by reciprocal of the slope of the other mirror. Why the reciprocal? That is because this second mirror it is converting the y axis into the x axis. So, that is why we do have the slope it is getting flipped. So, I should say this is equal to G M ratioed with 1 by R C with a minus sign. So, now in case if we want to really increase the gain, of course, it is having a limitation of the gain, we will be talking about that also. If you numerically see what is the value here, if you put the expression of G M into this equation, that gives us, that is I C, quiescent current I C multiplied by R C divided by V T, because G M into G M equals to I C divided by V T, and I C multiplied by R C, it is nothing but this voltage drop, DC voltage drop. So, and on the other hand the V T it is thermal equivalent voltage. So, we can say that maximum limit of this gain, it is the drop across this R C resistance divided by thermal equivalent voltage. And if we have the VCC supply here, obviously this drop across this R C cannot exceed that. In fact, that should be practically that should be lower than VCC, because we require some drop across this device. So, in extreme case, even if I consider say drop across R C equals to close to VCC, then the gain of the amplifier it is VCC divided by VT. So, that is the theoretical limit of the amplifier gain. So, that is what I said, that limitation of the voltage gain. In this circuit, because the GM it is good, in this circuit the gain value it is very decent, but in case if you want to further enhance, then we may look for some alternative. Now, what may be the alternative? Let us try to intuitively understand that what may be the scope of improvement of this gain. So, the slope of this line, it is coming from 1 by R C, and suppose this is the quiescent point. With respect to this quiescent point, if you want to increase the gain, naturally you may be thinking that suppose if I make the load line like this, which means that if I decrease the slope of the load line, which means that if I increase the value of this resistance R C, then from this analysis what we said is that voltage gain it is G M, which is the slope of the first mirror, and then divided by inverse of rather slope of the second mirror. So, if I decrease the slope of the second mirror, since it is coming in the denominator, so we may say that will be increasing the gain. So, this red colored mirror it is supposed to be increasing the gain. In fact, intuitively it is also clear that for the same kind of variation, if you see for this curve and this curve of the device, the intersection point it is here, and then the other intersection point it is here. So, it is expected that the corresponding signal it will be getting amplified like this. But what is the problem here? We are looking for a meeting point of the load line, which is much higher than whatever the earlier meeting point, and this meeting point it is nothing but the VCC. Now, if you are looking for higher value of VCC, which means that I am looking for higher supply voltage. Well, theoretically it is that is what it is, but practically if the supply voltage is more, there are two issues. One is power dissipation, it will increase. For the same quiescent current, if this voltage it is higher, naturally the power dissipation it will be a problem. And also instantaneously, if the output voltage here it is higher, then that may exceed the breakdown limit of the device. So, this may not be allowed. Some extent it is possible to increase the gain, but then you cannot make this VCC arbitrarily high to enhance the gain. So, the natural question or natural intuition it may be, or rather I should say smarter intuition may be, that can I increase this, rather decrease this slope without changing this voltage. Well, that is also possible. Maybe we can keep this point here and then we can try to decrease this slope of the second mirror, but then the corresponding quiescent point it should be coming down here, which means that I may be looking for a quiescent point somewhere here instead of this one, where the GM it will drastically drop. So, if I try to decrease this slope without changing the supply voltage, then I have to decrease the GM, and anyway the GM it is also coming in the expression of the gain. So, naturally it is not helping. Well, then what may be the solution? Suppose if I decrease this slope, but then if I do not allow this supply voltage to be increased, so we can probably terminate this characteristic here, which means that in case if we have an option to have IV characteristic which is not completely linear, but over this range it is linear, and then it is having sharp nonlinear to terminate to the available supply voltage. And then what we are getting by this blue line, blue load line, it is we are decreasing the slope of the second mirror, and at the same time supply voltage we are not changing, and also the quiescent point here we are not changing, which means that without changing the GM here, we are able to decrease the slope of the load line, and at the same time since the supply voltage it is remaining same, then we do not have any increase of the power dissipation, we do not have any fear of whether the device it will be entering into the breakdown. Okay. So, that is what the replacing this passive load by active load. Okay. Okay. So, anyway, so what we said is that limitation of the voltage gain of the standard CE amplifier, namely CE amplifier with passive load, and its gain it is primarily it is getting restricted by the voltage drop across this resistance divided by Vt. So, I should say AV max, it is the voltage drop across this RC divided by Vt, and that can be extended by going for some alternative of this. Okay. Similarly, if you look into the common source amplifier, on the other hand, it is philosophically it is same, only thing is that the IV characteristic instead of IC versus VB, now we have to see IDS versus VGS. Okay. So, as I said that for common source amplifier also we do have the similar kind of problem, to name with that, namely the gain, voltage gain it will be limited, and in this case the voltage gain in fact it is much lower than common emitter amplifier. In fact, we have seen that for in the numerical examples we have seen that Common emitter amplifier, it is having a typical gain of say 100 or more, whereas for common source amplifier for practical purposes, we have seen that with passive load the gain it is even less than 10. So, that definitely it is a serious matter. So, whatever the modification we are going to discuss, it is more significant for common source amplifier, if not important for common emitter amplifier. So, first of all, we do have Vds versus Vds characteristic curve, and here again if you plot the this is Ids versus Vgs characteristic curve, and in this case it is not exponential, rather it is a square law, right. But then philosophically again it is working as a reflector like a mirror, which converts the Vgs variation it converts into current. So, it converts into current, either you can see this way or this way, but basically it converts into the corresponding current variation. And then if you see the output voltage, which is supply voltage Vdd minus this IR drop. So, which is Ids multiplied by Rd, and mathematically we can say that V out it is Vdd minus Rd multiplied by Ids, and this Ids it is given here. And pictorially on the other hand, you may say that this is we do have Ids versus Vds characteristic curve, and if I consider device, it is initially in triode region, it was like this, and then after that it enters into saturation region at say some operating point. In case if the Vgs it is lower, then the corresponding IV characteristic it comes down like this. On the other hand, if it is higher, then the corresponding characteristic of the device, namely pull down element, it is like that. And then we do have the load line. We do have the load line, as you may recall, which is similar to the CE amplifier, and the point here, intersection point here, it is the supply voltage, in this case it is Vdd, and slope of this line it is 1 by Rd with a minus sign. So, here again this is working as the load line, it is working as reflector, and this may be say quiescent point, and in this case the expression of the voltage gain AV, which is Gm. Gm is the slope of this mirror, slope of this IV characteristic multiplied by or divided by slope of this characteristic. So, that is divided by 1 by Rd with a minus sign, or you can say this is minus Gm into Rd. And this Gm, if you recall its expression, this is Ids divided by in fact this will be 2 times Ids divided by Vgs minus Vth. So, it depends on how we express this Gm, but of course, this is one expression. So, this multiplied by Rd with a minus sign. Again this part, if you see, it is nothing but the drop across this Rd, and its upper limit it is of course, the supply voltage. In fact, practically it is lower, and all practical purposes we like to take this Id versus Rd equals to half of Vdd rather than trying to stretch to Vdd. and then depending on this Vgs minus Vth, which is commonly known as overdrive voltage of the transistor beyond the threshold voltage. So, typically this voltage overdrive voltage, which is Vgs minus Vth, that is much higher than thermal equivalent voltage which it was there for BJT. So, as a result, in fact Vgs minus Vth may be in the order of maybe 1 or 2 volts for discrete component. So, if I say that upper limit of IDS versus multiplied by RD is say VDD. So, we can say that this is the upper limit VDD, and so this may be that gives us the max of the voltage gain. Max of AV equals to 2 times VDD divided by whatever Vgs minus Vth, right. And since this part it is restricted by the supply voltage, then again it is having the limitation of the voltage gain. Numerically we have seen that if you take this is 12 volt, then practically we is to take IDS multiplied by RD, it is 6 volt, and then 6 multiplied by 2, it was that was 12, and the practical value of this Vgs minus Vth we have taken say 1 or 2, and that used to give a gain of only 2. So, sorry, used to give a gain of 12. So, again the conclusion is that with passive load the voltage gain it is really limited, and we are looking for its corresponding alternative. And of course, this is the corresponding analysis. If it is a passive circuit, passive load, then the corresponding load it was playing a role to define the gain. So, I will not be going detail of this one, but we may come back to the small signal analysis when we will be talking about the active load amplifier. Now, here again we like to replace this load or the load line characteristic. We like to get something like this, where the slope of this IV characteristic it is small, but then it should converge to this VDD point. So, we are looking for IV characteristic like this for this element. So, that the first of all the operating point remains unchanged, the corresponding current it will be the same. So, the GM here it will be the same. On the other hand, slope of this line it is getting decreased. So, if the slope of this line it is getting decreased, then this part 1 by RD part it will be getting increased, and hence there is a scope of increasing the gain, and also without that can be obtained without changing the supply voltage. So, we will take a short break, and then we will be coming back to discuss about the both the amplifiers with active load.